Okay, in this section, section 4.2, we're going to be talking about prime and composite numbers. And I have to warn you ahead of time, my pen is not working any better than it was in the last video for section 4.1. So I'm having some difficulties with it. And of course, you can't get replacement parts anymore because they're no longer making these. So we're just going to try and do the best we can to get through this. Okay, so in this section, we are talking about prime and composites, and you may already be familiar with these, and if you are, then that's fantastic. But there might be a couple of little things that you really need to remember, because a lot of people tend to forget the very first part of the prime numbers. Okay, so first of all numbers except one are either prime or composite. And when I say numbers, I probably should qualify that and say integers, because fractions are not considered prime or composite. Only integers, or what we consider to be whole numbers. Those are either prime or composite. Now, the number one, it's not considered prime or composite. It's kind of a weird being. Its only factors are one and one, which technically the definition of being a prime number is that it only has factors of one and itself. But because one is one and itself, but itself is one, it kind of falls into a gray area of the definition, and so they just don't consider it a prime number. They consider it an odd duck. So technically, the first prime number is 2, because the only things that you can multiply together to get 2 are 1 times 2, so 1 and itself. And then 3 is a prime number, 5, 7. And if you go along with that pattern, you might get the impression that prime numbers are all odd numbers. Well, okay, part of what I just said is true, but not the backwards of it. All prime numbers are odd. That is true. However, not all odd numbers are prime. So you have to be very careful. You can't assume that just because a number is odd that it would be prime. Because like 9 is an odd number, but it has factors of 1 times 9, but also 3 times 3. So that's more than 1 in itself. 25 is another good example of a number that is odd but is not a prime, because 25 would be 1 times 25 and then 5 times 5. So it has more than 1 in itself. Okay, so if a number is not prime, we consider it to be composite. And that means that it has factors other than 1 in itself. So the number 4 would be considered a composite number because it has factors of 1 times 4 and 2 times 2. So its factors would be 1, 2, and 4. Now, this leads us to something incredibly important, and that is the fundamental theorem of arithmetic. So this is what supposedly all of arithmetic is built on, the very core idea of it. And this, in your book, it says that each composite number can be written as a product of primes in one and only one way, except for the order of the prime factors in the product. Now, I don't really care for that particular wording of the definition. I think that it's been written better and said better by other mathematicians. So the definition that I prefer, and I think is the easiest to understand, is this one. And it says any integer greater than 1 is either a prime number or can be written as a product of prime numbers. I think that's a much better definition. So let's see what we're talking about here. Now, the easiest way to make sure that a number is prime is to try to do what we call a factor tree. And if you can't do a factor tree on it, then you know it's prime. But if you can do a factor tree on it, then you can reduce it down to its prime factors. So let's look at the number 260. And let's think of two things that multiply together to get 260. And this is where what we did last time kind of comes into play, because we can look to see quickly what will divide in evenly into that number by those divisibility tests. So looking at 260, because it ends in 0, we know that 10 will divide into it evenly automatically. So this 260 would be 10 times 26. Okay, now 10 is not a prime number. You can break it down further. In fact, 10 would be 2 times 5. Now when I'm doing prime factorizations, I always circle numbers once I get to a prime. So 2 is prime and 5 is prime, so I'm going to circle those to let me know that I'm done with them. But 26 is not a prime number. I know that because it's an even number. So if nothing else, I know that it will be divisible by 2. So 2 times 13 is 26, and 2 is a prime number. Now 13. 13 is not divisible by 2 or 3 because the numbers add up to be 4, so that won't work. It's not divisible by 4 because the last two digits are not divisible by 4. It's not divisible by 5. Since it wasn't divisible by 2, it can't be divisible by 6. And it's not divisible by 9 or 10. So this is a prime number. There is nothing. 13 is a prime number. Now when we write the prime factorization of the number, we always write it smallest to largest. So whenever I would write this, there are two 2's, so I would write 2 times 2 times, and then the next biggest number would be 5, and then times 13. And then to write it actually more compactly, we would write these 2 times 2's using the exponent. So that would be 2 squared times 5 times 13. This would technically be the prime factorization of 260. Now, the beauty of doing a factor tree is that you can choose any factors you want to, and you will still come out with the exact same answer. So, for instance, let's say that I looked at 260 and the first thing I noticed was that it was an even number. So I know that it's divisible by 2. Well, let's see, 2 times what gives me 260? Well, that would be 130. So 2 is prime, but 130 is not. So I know I can break that down further. So 130, let's see, well, it's even, so I know 2 will go into it. So 2 times what gives me 130? So if I divide 130 by 2, I get 65. 2 is prime, but 65 can be broken down further because it's divisible by 5 because of its last digit. So I know 5 times something equals 65, and that would be 13. So 5 is a prime number, and we know that 13 is a prime number also. So whenever I write this, I would write it as 2 squared, because there were 2 of those 2's, times 5 times 13. We got the exact same factorization no matter which two numbers we started with. And that's what they mean by that each composite number can be written as a product of primes in a unique way.